Now we have to talk about the quantum theory of Raman effect. To describe the Raman effect, it's essential to consider both elastic and inelastic collisions. An elastic collision occurs when a molecule deflects an incident photon without absorbing its energy. As a result of this, we can get unmodified Rayleigh lines. Consider a photon of energy h nu. After the interaction process with the system, the photon comes out as such. There is no change in the energy of the photon. Now we can get our unmodified Rayleigh lines. In the case of an inelastic collision, energy is transferred between the scattering molecule and the incident photon. Two different cases may arise now, which are the formation of Stokes and Antistrokes lines. According to quantum theory, a molecule can either absorb energy from an incident photon or transfer energy to it. Assume that h nu be the energy of the photon before collision. Half mv square is the kinetic energy of the molecule and its internal energy is E. Before collision process, energy of the photon is h nu. Then the kinetic energy of the molecule is half mv square. Internal energy of the molecule is E. These are all before collision. After the collision process, the energy of the photon is h nu dash. Kinetic energy of the molecule is half mv1 square. And the internal energy of the molecule is E dash. This is after collision. At constant temperature, half mv square is equal to half mv1 square. There is no major change in the kinetic energy of the molecules. Now the equation 1 is modified as h nu plus E equal to h nu dash plus E dash. From this we can write h nu equal to h nu dash plus E dash minus E. So this is equation number 2. H nu equal to h nu dash plus delta E. Now we have to talk about Stokes and Antistrokes lines. When a photon interacts with a molecule, the molecule absorbs energy and causes the molecule to move from a lower to a higher energy level. As far as the Stokes lines are concerned, the formation of Stokes lines is explained in the following manner. See, E1 and E2 are the two energy levels. E2 is greater than E1. Initially, the molecule is in the ground state. After absorbing energy from the photon, it goes to the higher energy level. Here, E be the internal energy of the molecule before collision. After the scattering process, E dash is the internal energy of the molecule. Now, E dash minus E is a positive quantity because the molecule absorbs energy from the incident photon. Now, delta E is positive. H nu, which is equal to h nu dash plus delta E. You may get Stokes lines. Now we have to express the process in terms of frequency. You know that E equal to h nu. Delta E equal to h into delta nu. Therefore, h nu equal to h nu dash plus h into delta nu. From this, nu equal to nu dash plus delta nu. Now we can write nu dash equal to nu minus delta nu. This is a condition for the occurrence of Stokes lines. Nu dash is lesser than nu. Nu dash is the frequency of the outcoming photon. The frequency of the outcoming photon is lesser than the frequency of the incident photon, which means that the energy of the outcoming photon is lesser than the energy of the incoming photon. It points out that the incident photon provides some amount of energy to the molecule. Therefore, the Stokes lines are present in the lower frequency region of the Raman spectrum. Or we may point out, we may expect the Stokes lines in the longer wavelength region. Both are same. Read out this. When a photon interacts with a molecule, the molecule absorbs the energy and causes the molecule to move from a lower to a higher energy level. This is possible in the case of formation of Stokes lines. Finally, the radiation that is scattered has a lower frequency compared to that of the incident radiation. This means that the wavelength of the scattered radiation is longer than that of the incident radiation. So the necessary condition for the formation of Stokes lines is nu dash equal to nu minus delta nu. Now we will go for the anti-Stokes lines. In terms of energy, h nu equal to h nu dash plus E dash minus E. This is the equation available with us. Here h nu equal to h nu dash plus delta E. In the anti-Stokes lines formation, initially the molecule is in the excited state, that is higher energy state. Suppose a photon is allowed to interact with the excited molecule. The molecule provides energy to the incident photon and the molecule comes to the lower energy state. Here, the initial internal energy of the molecule is E and the final internal energy of the molecule is E dash. The final internal energy of the molecule E dash is decreased. In this case, E dash minus E is a negative quantity. Therefore, delta E equal to negative. Here h nu equal to h nu dash minus delta E. In the case of anti-Stokes lines, nu equal to nu dash minus delta E by h. We know that E equal to h nu, delta E equal to h into delta nu. Therefore, nu equal to nu dash minus delta nu. Then nu dash equal to nu plus delta nu. This is a condition for the occurrence of anti-Stokes lines. The frequency of the scattered radiation is greater than that of the frequency of the incident light. This means that the incident photon absorbs some energy from the molecule. It is observed that the scattered photon has a higher frequency than the incident photon, which results in the appearance of anti-Stokes lines on the higher frequency end of the Raman spectrum. See, there is a Rayleigh line which is present at the middle. On both sides, you can get Stokes and anti-Stokes lines. Here, Stokes lines are more intense than the anti-Stokes lines. The potential reason is, at room temperature, most of the atoms are in the ground state. Therefore, the molecules may absorb energy from the incident photon. Suppose the temperature of the system is increased, the intensity of the anti-Stokes line is also increased. In this way, you may understand the formation of Stokes and anti-Stokes lines. That's all about the quantum theory of Raman effect.